In 1977, NASA etched instructions onto a computer chip and flung it past the edge of the solar system. And last year, for the first time, that chip started lying. Let me set the scene for you. It is late 2023, and the Voyager 1 spacecraft is cruising through interstellar space, the region beyond our solar system, where the sun's influence essentially fades into the broader galaxy. At this point, Voyager 1 is so far away that a radio signal traveling at the speed of light takes more than 22 hours just to reach it. You send a command, you wait nearly a full day, and then you wait another full day to get a response. That is the reality of communicating with the most distant object humanity has ever launched into space. For decades, this spacecraft has been sending back science data and status information like a dutiful explorer dispatching letters home. Engineers at NASA's Jet Propulsion Laboratory could read those transmissions, understand what the spacecraft was doing, and verify that everything was working as expected. Then suddenly something changed. The data coming back from Voyager 1 started looking like complete gibberish. Not silence, not nothing, but garbled nonsense that the team could not interpret. The spacecraft was still alive, still transmitting, still receiving commands and acknowledging them, but the actual content of what it was saying had degraded into something unreadable. Here is where the story gets genuinely fascinating. The team did not panic. They got to work methodically, and what they eventually discovered is one of the most interesting hardware failures you will ever hear about in space exploration history. Voyager 1 has something called a flight data system. Think of this as the brain that gathers all the scientific measurements and engineering data from the spacecraft, packages it up, and sends it Earthward. Within this system, there is a component called memory. Specifically, the flight data system contains a chip that stores the instructions the computer uses to format and transmit data. And one portion of that memory, accounting for roughly 3% of the total storage, had corrupted. Just stopped working correctly. The chip had a section that was no longer holding its data reliably, and whatever was being written there or read from there was coming out wrong. Now think about what this means in context. This spacecraft was built and launched in 1977. The memory components inside it are nearly 5 decades old. They have been bombarded by cosmic radiation for all of that time, operating in the extreme cold of deep space, running continuously without a single break or reboot for year after year. The fact that any of the original hardware is still functioning at all is genuinely extraordinary. The fact that only a small fraction of one memory chip has failed after 47 years is honestly impressive. But here is the problem. That small section of corrupted memory happened to be storing a crucial piece of code. The instructions that told the flight data system how to package and transmit data were partially stored in the damaged region. So when the computer tried to execute those instructions, it was working with corrupted code, and the result was the nonsensical transmissions that had the team scratching their heads. The obvious question becomes, why not just rewrite the corrupted section? And the answer brings us to one of the great engineering challenges of deep space exploration. You cannot simply upload a patch or push a software update the way you would on your phone or laptop. Every single change has to be written carefully, tested exhaustively, and transmitted across billions of miles of space. One mistake, one character wrong in the code, one unintended consequence, and you could make things dramatically worse. You could silence Voyager 1 forever. So the team had to think very carefully about their approach. The solution they landed on was genuinely clever. If the corrupted section of memory cannot store the code reliably, then do not put any critical code there. Instead, take the code that had been stored in that damaged region and redistribute it across other sections of memory that are still working correctly. This sounds simple in principle, but in practice it required an enormous amount of careful work. The code could not just be moved wholesale. The team had to divide it into chunks, place those chunks in different locations in the working memory, and then ensure that the computer would correctly reference all those different locations in the right sequence to execute the full set of instructions properly. Think of it like having a book where a chapter has been torn out and water damaged. You cannot restore those pages, so instead you rewrite that chapter, break it into pieces, tuck those pieces into the margins and blank spaces of other chapters throughout the book, and then add a trail of notes telling the reader exactly where to find each piece and in what order to read them. Now multiply the difficulty of that task by the fact that every instruction you send takes 22 hours to arrive, every response takes 22 hours to come back, and one error could destroy the book entirely. The team spent months on this. They tested their approach on ground-based systems first. They modeled the expected behavior. They planned every step meticulously. And then, in April of 2024, they transmitted the first portion of the fix. They waited nearly 2 days to see the result. And when the response came back, Voyager 1 was once again sending coherent, readable data, at least from the portion of the system they had repaired. Over the following months, they continued the process, gradually restoring the remaining subsystems one by one. By the summer of 2024, all 4 of Voyager 1's science instruments were back online and transmitting useful data. The spacecraft that had gone nearly silent in its communications was once again talking to its creators in a language they could understand. But let us take a step back from the technical details for a moment, because there is something much bigger happening here that deserves your attention. Voyager 1 is not just a spacecraft. It is arguably the most profound demonstration of human ambition and reach that has ever existed. When it launched in September of 1977, the goal was to perform close flybys of Jupiter and Saturn, studying these giant planets in ways that ground-based telescopes simply could not. The mission was designed to last maybe 5 years, maybe a little longer if everything went well. Everything went very well. Voyager 1 completed its primary mission and then kept flying. It kept transmitting. Scientists kept listening. And the spacecraft that was supposed to be done after Jupiter and Saturn became the first human-made object to enter interstellar space, crossing what is called the heliopause, the boundary where the solar wind essentially gives way to the interstellar medium, in 2012. Think about that. A spacecraft built with 1970s technology, using computers with a fraction of the processing power of a modern smartwatch, crossed into territory no human creation had ever reached before. Today, Voyager 1 is more than 15 billion miles from Earth. That distance is so large that it becomes almost abstract. Light, the fastest thing in the universe, takes over 22 hours to cover that distance. If you somehow drove a car at highway speed toward Voyager 1 without stopping, ever, you would not arrive for roughly 17,000 years. It is genuinely out there in a way that challenges our intuitions about space and distance. And yet somehow, we are still talking to it. Engineers at JPL are still sending commands and receiving data. The spacecraft is still powered by radioisotope thermoelectric generators, devices that convert heat from the decay of plutonium-238 into electricity. These generators produce less power every year as the plutonium decays, meaning the team has had to periodically shut down various systems to conserve energy. But enough power remains to keep the scientific instruments running and the communications link alive, at least for now. The power situation is one of the central challenges facing the extended Voyager missions. Engineers estimate that Voyager 1 may have enough power to continue operating science instruments into the late 2020s. After that, the diminishing power output will likely force the shutdown of the remaining instruments one by one. Eventually, there will not be enough electricity to maintain any of the science systems, and then not enough to keep the transmitter going at all. At some point, Voyager 1 will go quiet for good, sailing silently through the galaxy forever. But we are not there yet. And the fact that engineers were able to diagnose and repair a memory failure on a 47-year-old spacecraft traveling through interstellar space, using technology from the 1970s, sending commands across 15 billion miles of void, is one of the most remarkable technical achievements of recent years. It does not get the cultural attention it deserves, honestly. If this had happened with a Mars rover, It would have been front-page news for weeks. But Voyager 1 has been flying so long that people sometimes forget it is even still out there. There is a philosophical dimension to all of this that I think is worth sitting with. The engineers who originally designed and built Voyager 1 are mostly retired or have passed away. The people who are now diagnosing memory failures and rewriting code to save the spacecraft are working from documentation created by people who are no longer around to explain their thinking. They are essentially archaeologists as much as they are engineers, digging through decades-old technical records to understand how a system was designed and why, so they can figure out how to keep it running. This is not unique to Voyager, but it is perhaps the most extreme version of this challenge in all of human engineering. The spacecraft is so far away, so old, so resource-constrained, that every decision carries enormous weight. There are no spare parts. There is no possibility of physical repair. Whatever the engineers can accomplish, they have to accomplish remotely, across incomprehensible distances, working with hardware that is older than most of the people trying to fix it. What does this signal about us as a species? I think it says something genuinely hopeful. There is a human impulse to maintain connection, to keep reaching out into the darkness, even when it would be easier to let go. The Voyager missions have cost relatively modest sums compared to many other space projects, and yet they have returned scientific data about the outer solar system and interstellar space that no other mission has ever provided. The data flowing back from Voyager 1 and its twin, Voyager 2, has shaped our understanding of planetary science, solar wind physics, and the nature of the interstellar medium in ways that textbooks are still catching up to. There are things we now know about the boundary of our solar system that we would not have understood without these spacecraft. The heliopause, that boundary between the solar system and interstellar space, behaves differently than models predicted. The interstellar medium has characteristics that surprised researchers. These are not small discoveries. These are fundamental additions to human knowledge, delivered by two machines built with 1970s technology that were supposed to be retired decades ago. And so when Voyager 1 started sending garbled data, the people at JPL did not shrug and say it had a good run. They dug in. They stayed up late. They modeled the problem from billions of miles away. They crafted a solution that required splitting code across working memory segments and sending it piecemeal across the solar system. And they brought the spacecraft back online, delivering readable science data once again from a region of space that no probe has ever visited before or since. The story of Voyager 1's signal going haywire is really a story about human persistence. It is a story about what happens when the people who care about something refuse to give up on it even when the odds seem absurd. How do you fix a computer chip that is 15 billion miles away? You cannot. But you can work around it. You can find a path forward that does not require fixing what is broken, but instead adapts to the damage and roots around it. That is engineering. That is problem solving at its finest. And here is what I want you to leave with. We are living through an extraordinary era in space exploration. New missions launch regularly, new discoveries happen constantly, and it is easy to let older stories fade into the background. But Voyager 1 is still out there, still transmitting, still scientifically productive, still adding to our knowledge of the cosmos. It is a monument to long-term thinking and patient science. It is proof that investments made 50 years ago can still pay dividends today. The next time you feel impatient about something, the next time you feel like progress is too slow or results are not coming fast enough, think about the team at JPL waiting 44 hours for a round-trip communication with a spacecraft. Think about them troubleshooting a 50-year-old computer chip from billions of miles away. Think about the months of careful work that went into crafting a software fix for a machine that was launched before most of the engineers working on it were even born. Voyager 1 will eventually go silent. Physics demands it. The power will run out. The signal will fade, and humanity's most distant emissary will continue its journey through the galaxy without ever speaking to us again. But until that day comes, the people watching over this mission will keep listening. Keep responding. Keep finding creative solutions to keep the conversation going. And that is pretty extraordinary. If you found this story as fascinating as I do, there is a lot more to explore about the Voyager missions, about what the spacecraft discovered during its planetary flybys, and about what scientists hope to learn from the remaining years of operation. The universe is enormous, our knowledge of it is still limited, and old machines sailing through the dark still have things to teach us.